Yes. Okay. And now window or technical. I'm presenting. You're presenting. Yes, still present. Okay. I hope this works now.
Yeah.
Okay.
So maybe you wanted to.
Yeah.
So that we see people actually.
Yeah, but then we cannot move on. So
Anyway,
this thing only has one monitor, so you need to pay me more. So.
Sorry for our friends.
No worries. So yeah, I did prepare a few things, and I wanted to talk about the journey because OpenCloud did not start as a Go application. As you may know, our background is actually from OpenCloud, which was a PHP LAMP application, classical LAMP stack. And I would like to talk about all the things that we do to deliver a software, even change probably the architecture underneath.
maybe.
It's using one of the sync lines of either project.
Okay.
Yeah.
It's a sync client.
Desktop, mobile, Android,
Okay.
iOS.
Yeah.
So because that's what people see.
Okay. Okay.
And so that's really interesting. So I would like. So how can we start? Probably best by. Should we just go back to the old technical stuff and then continue? Yeah.
Yes.
So, as you may know, OpenCloud 10 started as a classical LAMP stack, although it's not really LAMP. It could be either Apache or Nginx, could be SQLite, MySQL, PostgreSQL, Oracle. It was a zoo, and it was terrible to maintain and test everything. So we had a test suite of, I think, 1,500 unit tests, and you can see what it looks like in the OpenCloud 10 code base as well as the Nextcloud code base. They still use the same test suite. Of course, with time, more tests were added. There are even end-to-end tests, but the classical stack usually had a web server, a cache, and a database. Of course, they don't need to run all on the same machine. There would be typically 2 or 3 instances of each, and underneath there had to be some kind of storage. That works and scales pretty well to a certain degree. So
still, we decided it was not running well enough for us.
So the first thing that we hit was the max int in the databases. That was actually something that customer of us actually printed T-shirts on. I hit max int. So that was fun, and that was the old days. But the bigger or more interesting customer was CERN, because they actually have a software-defined storage written in C++, which is called EOS. That's your run-of-the-mill software-defined storage with a split of metadata and blob storage.
Has anybody heard about EOS? No? Okay. That's unfortunate. So if you're in the software-defined storage area, EOS is worth
Anybody
checking.
heard of Lizard FS? Moose FS? Sauna FS?
Sauna FS.
It's the spiritual successor to Lizard FS and Moose. I think, Moose FS is the old one. Then came Lizard FS, and then came Sauna FS. And actually, the ideas of those are actually something that influence EOS heavily, because CERN is one of the typical places of not invented here syndrome. They will rewrite everything according to their needs. So they rewrote a Redis with Raft consensus algorithm and all this. So if you need something rewritten, look at them.
Go to CERN.
Go to CERN. If you want to do that, if you want to get paid for that, so just go to CERN. They're looking for interesting people. So nice place to work at, and so we visited them often, and it's really a great place. So just keep that in mind. And they're really some smart people, and one of the younger there back in 2016 or something had a look at the at Go. This is where we enter Go territory. He actually wrote a benchmarking tool to benchmark several file sync and share solutions like OpenCloud 10, or it was OpenCloud 7 maybe, IDEO, if anybody has heard of that, and CFile. So those are the contenders, and he wrote an abstraction layer in Go, which is basically, in the front end, there was a gRPC API, and in the back end, he implemented proxies to these different storage systems or file sync and share solutions.
And all of them, maybe to add, all of these systems were completely different. So CFile is using some algorithm that splits up files into 4K blocks, as Dropbox does, and IDEO does something completely different, and OpenCloud does the metadata into databases and files into file systems.
Yeah, so they really have the research community does what they do best. They do research and actually scientifically try to find out which software-defined storage solution out there solves their problems best. And the desktop client, which he wrote, is actually the only desktop client that they didn't manage to break, or the sync algorithm. That's something that they're still proud of.
After years of debugging and things.
And finding bugs in what?
In everything.
That really was, it's a great partnership, and they have helped us solidify the clients, but they don't like databases because in their instance, the CERN EOS storage is filled with the Harden collider, which floods the thing with the data, and the amount of changes that occur and they're added lead to some database rows running hot in OpenCloud 10. The problem there is that for the syncing algorithm, which is why I mentioned, we need to propagate changes from deep down in the file tree up to the root so that the desktop client can see, this directory changed, I can navigate into it and then find which file actually changed. So I can sync. However, if you need to update the same database row over and over again, that becomes a log contention. And if you add sharing, where multiple people can work on the same tree, the root becomes even harder. So they said, can't you do something so that we can, replace your database layer with whatever we want?
I think we should add that you can find better and more smart database designs than the one that OpenCloud 10 and Nextcloud have. So there's one very central table called file cache, and that one
it's called a cache, but it's not a cache.
Yes, it's not a cache. It's a
and it's the source of truth.
It contains everything. It contains the world, and whenever something is changed in there, especially files that were shared to many people, because unfortunately these single table contained an entry for every share for every person. So then you end up with many changes in the same table, and that gave interesting log conditions, which block the whole thing, and the whole database is going nuts.
I bet the world has improved and things have become better. But the interesting thing was that the young guys at CERN actually, out of their framework, their testing framework, which is called Claw.io, it's no longer used, but they started with that architecture, and I think that evolved into something called the CS3 API, which is a set of gRPC APIs, and RivaD is the reference implementation for these CS3 APIs. The boxes that I put here should just represent different services, that gRPC services, gRPC endpoints, that they run in the same process, and they actually run, I think they run 3 bare metal nodes. They don't have too many users, probably 3,500 active users at the same time, but they have petabytes of data. And that's just the problem. So they can actually deal with probably 3 or 4 physical nodes. They did not, they wanted to move to Kubernetes, but over the past years, they just said, no, we'll just stick to 3 nodes and that works.
So then, maybe we should, on a more general view on the product, we see very, very different patterns of how people use OpenCloud or OpenCloud. So there are organizations like CERN with tons of data and relatively little amounts of users. And then there are other use case scenarios with a lot of users with very few data and so on and so on. And that makes it really hard to optimize for a special case. So that's why we always have to think about many scenarios in which we have to be efficient.
So this RivaD is basically, it implements the APIs that OpenCloud 10 provides for the desktop clients and the web UI, and internally it just talks to their software-defined storage. But it has a predefined set of APIs that make up a file sync and share solution, like users, groups, sharing with public links, sharing with groups, and all these different aspects, all these different boxes here. Then came along another big player in the research community, which is RNet, which is the research network in Australia. They manage universities and bibliothecaries. It's a huge network, similar to the Deutsche Forschungsnetwork here. They said, we want what CERN has, and we're going to throw money at you. And if you don't deliver, then we'll just go to CERN and fork whatever they have and build our own product. So that was kind of Zuckerbrot and Peitsche. I don't know how to translate that in English. But that was interesting, and we actually researched at the time of other ways to make PHP scale better, because there were other solutions with an event loop, which is something that you may have heard of, like React PHP and several others. But it turns out that all of these other solutions wrote their own MySQL and Redis driver because they couldn't use the stock drivers because they don't run in an event loop. They were blocking too much. So we came to the decision, okay, it's probably a good idea to actually embrace that. So we sat down with the certain people and discussed about the architecture, what they did. But we said, I don't know if you know OpenCloud 10 or Nextcloud, you can put other storages behind that. So you could store your files on Google Drive, you could store your files on Dropbox, on different other storages. So we said, we need to be able to change storage layers because none of our customers will have a CERN EOS storage. So we need to change that. And that's then with the things that we discussed with CERN, we came up with some changes to those CS3 APIs, which is actually, let me probably explain what CS3 API stands for. Cloud Software Sharing or Service Sharing Collaboration. It's a project, look at cs3community.org, where all the research institutes basically sit together and discuss how they provide a file sync and share service to their students and research staff.
Yeah.
And that's a really great conference for people very in-depth on storage topics. That's really great. Yeah. So we came to a good decision and started working on it. And it was actually a small prototype called Nexus. I do have to mention that. Because we thought that we could have something ready in probably 3 months. And then it took us 2 years.
2 years?
The first, I don't know. Interestingly, as I'm trying hard to push that. We didn't do the rewrite, right? So that was CERN. They started that. We just iterated on that. The RivaD has been running in production at CERN for already 3 or 4 years at that point. And we just iterated on that and changed the APIs. And during that process, we noticed that, hey, all these individual shares between people is just a mess. Our product manager has a really nice picture of spaghetti code or spaghetti in the fridge. I don't have that with me, unfortunately. But it turns out that the spaces concept that we have in OpenCloud and that OSIS also was something that makes sharing a lot easier. And
let me explain a bit more about the problem of sharing. So in OpenCloud 10 times, sharing works like an individual user has a folder and shares this folder with other people, with groups or with individual people or whatever. So all the share receiver can see the content of the single folder of this simple single user. So the problem comes when this user is leaving the organization, because usually you want to keep this share to keep people productive in their everyday's work. So what happened, for example, in the OpenCloud company, we were still having the user of the very first user on the system in our company OpenCloud, because we couldn't remove him. And yeah, we were trying to solve that, because also shares often are a reason for performance bottlenecks and complex code, because everything is basically multiplied by the number of people who receive a share. And we've found then a way called Spaces, which is more a collaboration space. So it is a file space, basically like a folder, which is owned by the organization and has individual users from the system who organize this space and can add other space managers, how we call them, and things like that.
It's more like this Samba group drive or Windows Network shares, where you have a drive for all the people, for a group or a department.
Yes, the actual really new thing is that it's not attached to a single user, but can change the management and the ownership. It doesn't sound very revolutionary, I agree, but it really changes the game a lot, because basically it reduces the number of space of shares that individual people do a lot, which is good for the system hygiene, because now we have spaces for work groups to work on, and users have their own personal space, which now really is personal and not longer something where everything is somehow spread.
And it was about hygiene and spaces, and
I can imagine that you wanted to talk about more spreaded spaces all over the internet.
Oh, you're a sea of spaces. That's your idea.
Yeah.
So one of the things that had to change for these spaces to work in OpenCloud 10 and in Nextcloud, I don't know if it's still that way in Nextcloud. If you know it, correct me if I'm saying something that doesn't work that way. If you create a share, if you receive a share, you can actually put the share anywhere in your personal tree. So that puts the stress and the management on the end user. But of course, if you have like management departments, then there's typically a rigid structure in those department drives. So the sharing with the spaces actually leads to a change where the desktop clients and the mobile clients and the web UI will give you a list of drives that you have access to. It's that you no longer have just access to one drive or your personal files, where whatever has been shared with you is mounted somewhere. In OpenCloud 10, there were configuration options where you could jail shares into a shared folder. That tidied up this a little bit. In OpenCloud, in OSIS and in OpenCloud, this has become a first-class citizen. So every client has been taught that a user has access to more than one space. And regarding this sea of spaces that I mentioned, is that in the future, I see a way where clients no longer need to talk to just one instance, but they can directly talk to any instance, like a federated instance, federated sea of spaces. But it's far future.
That's far future. But back to this picture, maybe there's one thing on this picture that you don't see anymore. What is it?
What is it?
Yes.
Yes.
So while we were over it, we decided to drop the database. because we were so fed up with debugging database problems at customer sites.
We decided to write our own file system.
We decided to try to find other ways without a database. And the idea is really that, as I said, so most of the support cases that we saw in the company were really due to database problems. Not only int, how do you say? Mux int violations, but all kind of things. In Oracle is the worst, and people were deploying on SQLite and wondering why it was slow and stuff like that. And but also, I don't know, maybe some of you maintain Galera clusters or big Postgres things. It's a lot. So we try to become much more simple in the whole system setup and went without database. At least database that is persistent and needed and a single point of failure.
Was this a difficult decision to make? Because
yes.
Oh yes.
Because
there was
I know some places where also databases are really like not the first thing that you go to manage storage. So I sympathize with the idea, but I feel like it's not a common idea.
It was, yes, exactly that. It's not a common idea. You have to argue with most developers who are used to build up systems where metadata or structured data in general goes into a database. And then often it's a really good idea to do that.
Yeah.
Sometimes it's not. There's this split brain problem that we always had in the old architecture, writing metadata into the database and writing a file blob. There's time in between, and there can happen everything. And it happens if there's enough.
If enough time goes by.
Enough time or enough events go by, it happens. Everything happens at some point. So yeah. So we now use basically the file system as a database, which, I mean, a file system can be seen as a database as well, of course. And yeah, and a lot of caches.
And a lot of caches, yes. So I had the crazy idea to put a file system on top of its head and store metadata in there. The initial idea was to actually just write metadata into extended attributes, but it turns out that was just too slow. So we added caching, and then turns out that having so many syscalls is still a bad thing with Golang. So we started to just write message pack files. And things became a lot smoother. And that's what we currently do. So we store metadata in message pack files, and every file has its own unique ID, and that doesn't change over its lifetime. So even if you, in the web UI, overwrite a file, it'll have the same file ID. And that allows us to attach sharing information to it, which we currently store just in a JSON file. And we just make sure we are synchronizing and e-tags that we don't overwrite changes in that JSON file, and that works. Of course, it doesn't super scale, but since most of it is cached, that actually we can actually verify that that is not our bottleneck.
Yeah. So maybe
testing
later.
This is the testing slide.
This is testing. What needs to be added is now we managed to get away from the database, but the work has to still be done. So we shifted a bit towards the file system and need a more stronger file system now. So NFS, for example, is not a good idea to use. Everybody knows that, but it's turning out here as well. We need NFS version 4, and it needs to be tweaked and things like that. It's here on this slide because this is an example deployment that runs actually the biggest installation of OSIS, of OpenCloud Infinite Scale. That was the successor of the CERN Riva that we built in OpenCloud back then. Yeah, but no testing maybe.
So if you want to run this, use the no AC mount option for NFS. That's the only thing that's better.
Yeah, which is
no caching,
which is terrible.
Because then we run into inconsistencies, and we need consistency so that every pod that accesses the file system sees the same data. It's a big important thing, but probably you wonder how we managed to actually evolve the product over from one language to a different language, and from one architecture to a completely different architecture. So the interesting thing is that OpenCloud and Nextcloud have this huge test suite, and we actually run the same test suite against the new implementation. And we continued adding corner cases that we now face, and we actually got rid of features that we no longer want to support. We just said, okay, we found out, okay, these tests are failing. Do we really want to support that? Yes or no? And we cut a lot of that. For example, disk encryption. We don't do that. That's something for the file system. Not yet.
So we started with the test environment. We started on day one, actually. So not after 2 years, we started to look into our test suite, but we started even before we implemented the new system. We set up the whole testing and had an interesting file that was called expected failures, where all test cases were in the beginning, and then we ticked off the ones that are not longer expected to fail. And the goal was basically to get the whole file green and run, and succeeded. And I don't know how far we are now, probably.
Well, the product itself, the features that are currently there are a well-defined set. And if somebody wants to change that, he needs to go through our PO, PM, product manager, and he will often say no, which is a good thing. So don't underestimate having a good product manager.
Absolutely.
So please help him. If you're working in any company, just help your product manager. That saves, yeah.
And that test suite also gave us the opportunity or the way to stay with the clients that we had, Syn client and mobile clients, and also for a certain degree the web client. They all were depending on APIs that we kept stable basically between the two generations of the product. And now we are moving very slowly forward with new APIs for like Leipzig Gophers and things like that. Sorry.
Yeah, exactly. So OpenCloud 10 is all web dev. I don't know how much you still have to do with web dev. Okay. CalDev and CarDev, every one of you uses that. I don't know if you do know that, but every calendar and contact solution uses Apple, at least under the hood, uses it.
Yeah.
And the Google Calendar also exposes it.
Yeah.
So web dev is for files, for listing files, and the only API that we added to it is the LibreGraph API, which we call it, to list all the spaces that a user can access and manage that. So there are it's more JSON-based. It's OData, if anybody knows that. And Microsoft actually started that. They have put every service that you know from Microsoft behind this, an API that works exactly the same in regards to pagination, joining. Basically, it's SQL on the web, which is what OData does. So it's pretty neat. If you want to write an API for Microsoft, just do that. Great. So that was the inspiration for
LibreGraph.
So
we had the crazy idea that if we copy the Graph API from Microsoft that is used in all this Office 365 and Teams and stuff, maybe we come to a point where free software solutions can replace the whole stack because we have servers that provide these APIs.
It's a bit of a far stretch. It's a stretch goal. Okay.
I mean that's how we in the open source community look at things, right? We have to start somewhere and try things and see if we can succeed or not.
Anyway, trying things and see if we can succeed or not. So this is the deployment at the Bavarian School, and I have to distance myself from it because I was not taking part in that. So it just was not my idea. So what they came up with.
So maybe stop the project of Bavarian schools and Bavaria. Bavaria is a bit more centralized, as you might know, here in Leipzig. Bavaria is basically a kingdom. We have our king, called Söder. Not easy, but well. So in Bavaria, there's a school cloud system that is offered to every school in Bavaria. In most other Bundesländern, schools have more individual freedom to pick solutions, but in Bavaria, really every school can choose to use
For free.
for free. So
They can choose to use another solution, but then they have to pay for themselves.
yeah,
Just not really a choice. Okay, there are schools that use a different system.
So we built a system. Obviously, that was a huge success for back then in OpenCloud times. Of course, we were very proud. I mean, imagine that at some point you bring your free software project that I basically started on a KDE conference with Frank Karliczek on that. And at some point you end up with deploying it to all Bavarian schools. That's cool. So yeah, we were working hard to make that
1,500 schools, and every week. So deploying a school took some time. So it was constant deploying of new Kubernetes clusters, and there was a cluster of Kubernetes clusters and a tool that's called Gardener, and the name's like crazy, but okay. So I don't know if you've heard of that. So that was tough time, and actually, it's not only that we had a new product and a new language, but we actually had to build a new team, and not only a new development team, but also support team.
Yeah.
So the whole OpenCloud company had to change. There was still the OpenCloud 10 company, the OpenCloud 10 code base and customers that were using it. But if the Bavarian schools knock at your door and say something needs to happen now, then you have to jump.
It was basically 1.6 million users on the system, a centrally managed IDP, where this, I think, 3,500 schools.
Yeah, that was planned for, and they were estimating 80% of actual adoption, and when we left it, they were at 60. So
yeah,
maybe there are now more. But
and they planned for, I think, 48 petabyte of data in the biggest.
Just ask questions.
This was around early before the pandemic, shortly.
No. It was during.
No, it was after the pandemic.
After pandemic,
which is a great topic because the pandemic. The pandemic.
So each school had their own Kubernetes cluster, or
no. Every Kubernetes cluster is hosting, I think, 5 schools. So
depends a bit because schools are really different in size, also in Bavaria.
Even in the kingdom of
Bavaria, there are very small and bigger schools, and there's a bit variety.
They range from 150 users to 3,500. The biggest school was, I think, 3,500.
Such a beautiful picture, Bavarian landscape, village, and the Kubernetes
Yeah.
cluster.
Yeah.
Yeah, I mean, at least it is kind of future driven. What Söder always claims, in Bavaria we do this Lederhosen and laptops thing, and but in this case, I think that is kind of how would I say?
The clusters were running on premise inside the school itself, or was
No, central data center in Germany, not in Bavaria actually. So still, but in a German data center, which is a challenge also, or was a challenge.
Say the name. Why can't we say the name?
We can. Plus Server.
Yeah.
So Plus Server was actually hosting that with 2 Standorte. Locations of
at some point they were driving around NetApp storage machines from Hamburg to Cologne, I think, from one data center to another, because they had underestimated the load that we would put on the servers.
Yeah, we were heavily debugging iOS
data center
numbers, how much access we do on single files on the poor NetApp that was behind it, and things like that. So
I mean, we replaced the database with the file system, so where would the IOPS go?
I can imagine that also a challenge might be that the school needs a good internet uplink, and given how bad internet connections in Germany are, especially uploads, this could be problematic.
Yes.
maybe.
Yes.
So I have never ever had a project requirement specification that was as good as that one. I have to absolutely give them credit. It's super cool. They came up with load tests, which brings me back to the COVID times, because they noticed that, oh, we have to actually do online teaching now, and somehow the systems cannot hold the load and don't manage the load, so they are failing. And we need to make sure that whatever school system we build and pay for, that has to survive a load jump of X. And X was precisely defined. In 5 minutes, it had to survive a load jump, or I don't know, I no longer remember, but that was really beautiful.
Yeah.
I really like it.
So anyway, the people on that project had a lot of lessons learned during pandemic and were really also fun to work with.
Yeah.
It was cool. Yeah, interesting usage scenario anyway, because this whole system is only active between 7:30 and 1600, and the rest of the time it's basically dead.
Yeah.
So,
which is also the problem. So if you look at this, I initially, so if you look at this, CERN had deployed all the different services, gRPC service, in one process, and someone thought that it was a good idea to put every service in its own pod, which technically does work if you have thought of everything regarding service registry and pod lifetime, pod healthiness, anything that's related to Kubernetes, which we obviously didn't at the beginning. We actually, technically we use Go Micro as a framework for writing microservice applications.
has anybody heard of Go Micro?
Just,
Yeah.
just the name.
Meanwhile, it's safe to say that it's dead. I don't know.
Me
Maybe
neither.
on live support. But yeah. So we had discussions with the lead developer of Go Micro as well, and we were finding our first ways through, okay, how do we build a microservice architecture, and what kind of service registry do we use? And it has a way to integrate with the Kubernetes service registry or control plane. But in the beginning, we didn't know where to put what, and that led to every pod in every school talk to every other pod in every other school and listen to each events from the service registry or from the Kubernetes control plane, which led to etcd going down and actually killing the data center. So we had so much traffic that we actually brought down the data center, which was not only for us a pain, but also for other customers. So yeah, sorry, anybody listening to that, sorry. So then we deployed our own nuts and used that as a service registry, because our Kubernetes DevOps said, okay, whatever you do, just do your own service registry, don't use Kubernetes. Okay, so and then it turns out, okay, how can we actually see if the system is behaving correctly and survives this load jump that's defined in specifications? So we had K6 as a load testing tool. Who's using K6? Everybody else use it.
Yes, K6 is
Really awesome.
is magic.
Use it to test your systems automatically, and it's really great. And we had continuous sessions and check-ins where we would run a load test for 4 hours with the defined load profile, with different scenarios and different user profiles. things like, okay, users who would up and download stuff, users who would manage files, all these things. And we could notice and could see how the whole system behaved and how fast it was. We could see like, okay, when is the load jump happening? When is a new node added to the cluster? How does that affect the traffic and the whole load? So that was really great to learn. And personally, I became more and more frustrated with the overhead that we were having due to the number of pods that we have. I didn't bother to put specific service names on these boxes because it's completely irrelevant. Because we decided to say, okay, let's probably go back to something more like the traditional LAMP stack. So we have an API pod that runs all the services that handle request-driven traffic. We have a backend pod that handles events that are handled by a NUTS cluster in Kubernetes as well. And that's far more traditional, I would say, but it scales far better. And in this deployment, I mean, it's quite so the requirement is, okay, at night it should not cost any money because nobody's using it, but it should be able to scale to 3,500 users in 5 minutes. Whoa, okay. But we want to be, we have the requirement that it has to be highly available, HA.
And we are not estimating, we are counting CPU cycles here on the bill.
Yeah.
So it's not like, okay, the system is going down or good. It's really on CPU cycles.
Yeah. So the challenge was, how can you scale this down? So every school,
Down means the nodes in the cluster.
the number, how can you scale the number of pods down to the least amount possible? You cannot scale down to 0, unfortunately. Or at least not in that architecture, not in the number of pods that we had. You can reduce the number of CPU cycles or the CPU limits and memory limits, yes. And that was basically what we tried to do to, okay, how many milli CPUs do we have? How many megabytes do we have to use so that the system doesn't die immediately and scales down pretty well. Unfortunately, since we had so many pods, we had the overhead of the Go runtime and other things in every pod. So we were eating 2.1 gigabytes of RAM for every school, and we could not go below that. While if you run that in a single pod, you are roughly at 230, 250 megabytes. So that's an overhead that you couldn't go below with that architecture. In idle. And that's something, that's an overhead that they are currently paying every night, which I'm not happy about. So we decided to change that architecture to now we have 2 pods, and that can scale very differently.
So there's more than one service in one pod.
So yeah, what are services? What are pods? So
Yeah.
so the way that the architecture, the software is cut is there are multiple services and they are exposed as a gRPC endpoint. They all have their own port open, and but if you run them in a single Go process, then the memory usage is far lower than if you would start every process in its own own process, and every service in its own process in its own pod.
Yeah, it's like the old type of application service Java. So have you one application server for one service, then there are tons of gigabyte, and then was the reason, I guess, to build these application servers. There's several one in one, but
and then they all deploy their own.
But it's like a trade-off between
exactly
the number of.
So maybe
we merged a couple of services into a single binary, like
Well, it's okay. Yeah, that's an interesting topic. So OpenCloud is already a single binary, and it has always been a single binary, which was one of the things that drove us during the development. It should be easy to test and deploy and run in. So you just run OpenCloud server and it runs. Great. Okay, you have to run OpenCloud init first, but yeah. That allows us to run a single process. That is also how we are running the Docker post deployment. It also just uses the same binary. It just starts all the services at once, and that's just one process. Technically,
with all services.
with all services, but they are still listening on different ports.
Yeah.
They do not communicate in process.
No, they communicate via TCP.
Okay.
You can configure to use Unix sockets, but somehow they haven't let me do that. So they haven't let me productize it. But I will sneak that into the Kubernetes deployment, because there I no longer need to talk to other pods, because the services that are running inside the same pod can just use Unix sockets to communicate. And maybe in the future we'll just get rid of that.
Like, why not calling functions directly?
Yeah, that would be great. Yeah.
Because we are
because
microservices.
the old idea was, we have microservices, so we need to use microservices. It's
Yeah.
obviously wrong.
It's a learning curve.
Yeah.
It's really a learning curve. Learning by
So today you would just call the functions in code without doing microservices.
would we
So there are certain, so the learning that the CERN guys had was that, okay, there are some APIs that we should define so that we can exchange functionality. For example, they have a different user management than we, so they need to exchange that. How do you call that? Okay, you use a gRPC API. gRPC isn't bad, and it's actually really fast. Of course, you could save even more. You could save a complete trip down and up the TCP stack by just doing in-memory calls, of course. And there are things like GoMicro has a way of making an in-memory call in place of a gRPC call. But we didn't look into that, and I think we will never do that, because I think we would rather throw out GoMicro first. And get rid of it, because so what we do in the new Kubernetes deployment is we no longer use the service registry, or we no longer use our own service registry. We just now again use Kubernetes and DNS-based routing. Yes, there is a problem with gRPC calls, because obviously you have to get notified when the new pod arrives, so you have to do some things, do some tricks to make HTTP2 work in the Kubernetes cluster, but that is easier to do than having to rely on a framework internally. So I think we will try to get rid of that, because DNS-based routing not only works in Kubernetes, but also in Docker and on localhost.
change topic? Meanwhile, we are now here on this slide. Leave it.
I want to go forward.
Now you see it's OpenCloud.
Yeah.
So the story behind that is, before we were OwnCloud and had this school cloud deployment, and once OwnCloud was acquired by a US company called Kiteworks back in November 23. And as these mergers are often, that brought in a completely different company culture and view on open source and all these things.
Yeah.
So what we then did is we quit.
We sat back and watch
Yes,
And you guys had to take a lot of flack and blame.
Yeah,
from
I was
the guys
not really watching.
you stood on the front line, and I still have to thank you for that.
So yes, so it turned that this is not something we want to. Many of us from the engineering team and from other technical teams, that was not how we want to work, and that's not why we drove free software for so many years, and open source software. And
we found each other.
Yes, so we quit individually and found a new job in a new company. individual, of course. And that the new company is Heinlein in Berlin. I don't know, maybe you know it. It's mailbox.org. Yeah, Heinlein, Per Heinlein. He is long-term activist in secure communication. Mailbox.org is one of the big German mail provider for digital sovereignty. And he actually built up a new team to continue to work. And obviously, OwnCloud Infinite Scale was open source code, so we were able to fork it. And yeah, do a fork and name it now OpenCloud. And forking is an interesting topic we can talk over beer. We learned a lot of lessons of how to fork a project, but we kind of managed, and that's why that's now OpenCloud. I wanted to insert this little side story.
Mm-hmm. Yeah, that's a really good story for later.
Yeah.
So there are some changes that we may want to do. We may extract a proxy port, is what it's called. It's called a proxy service. You may know it as a gateway API. And we will use that, or I hope we will use that to shard requests and shard an instance. We are working on multi-tenancy. And then we can route requests to the correct shard. And that should allow us to scale out horizontally far better. And on the other hand, you may see that there is no longer an NFS storage here. I would like to get rid of that. And
everybody would like to get rid of it.
There are ideas, and we discussed just minutes before we came here. I discussed it with him, and that's another topic for beer, because the options are there's a lot of options that we could take. However, this might be the way we will deploy OpenCloud in large scale infrastructures for hosters or big companies. But OpenCloud still is an open source project, and a lot of people use it at home. And that's what we have the Docker Compose deployment for. And you may see here, there is an OpenCloud Docker container, which will run OpenCloud all in one. And obviously you need Collabora, Tika, OpenSearch and others if you want. So it's quite a zoo, but that exists in the Kubernetes stack as well. So if you want to run OpenCloud in a Kubernetes cluster at large scale, you need to have a scalable Kubernetes Keycloak cluster. You need to have a scalable NATS cluster. You need to have a scalable OpenCloud cluster. You need to have a scalable Collabora cluster. You need to have a scalable antivirus solution. So that's a lot, but that's also what makes it interesting. The small solution for that will run on home machines. However, we found the biggest differentiator is that we can natively talk to a POSIX storage. So it's not about having an object store, because most people at home will actually just use a POSIX store with whatever solution they have, probably their music sharing or whatever.
So this POSIX storage, the nice thing is migration is really easy. So what you do is you set up your Docker Compose file, edit.env, start Docker Compose, the thing comes up, you see everything runs, you shut it down again, you copy your files into the right place, the whole tree, you manage to set the correct user, group, and permissions, which is the only pitfall, I would say. And you start your cloud again, and it's there. It has all the files and is calculating stuff in the background, is doing the Tika indexing and all that stuff. So it's really easy to do migrations from other clouds. Yes, that's the POSIX thing. What it does, it looks at the storage tree and uses file system notifications from normal file system in Linux, like XFS or Btrfs or whatever. There's iNotify in Linux that works. We also have support for bigger software-defined storages like CephFS or GPFS, which is IBM.
Does anybody know GPFS?
GPFS.
IBM Spectrum Scale?
Yeah, Spectrum Scale. It's now called Spectrum Scale. Yeah. It's IBM technology. Huge, expensive, and awesome.
And works awesome.
Yeah, and this also provides more change notifications for the file system in clusters and all that. We can connect to that, and it's really magic because you go with your VI in, create a file somewhere in the file tree, and in your web interface it just pops up and is there. So that is, no other system can do that. We built that, and it's nice. And let me rant about S3.
Yeah, I just wanted to ask about S3. What is like some default system that you use for like?
Depends on the size of deployment. So if you
typically a customer already has an S3 deployment.
But S3, everybody wants S3 because it's so simple. But they want features of file systems like IBM technology.
Yeah.
So S3 is just simple. It doesn't have advanced features. So also we cannot add so many extra advanced things to S3. So
S3 does a lot of things nicely, and you could use it. But then if somebody decides to just rename his whole project folder, that takes ages. Why? Because an object store is not a file system. You have to copy every key and delete the old key, and that takes ages if you have a lot of small files. Object stores are not made for small files. Other than Seaweed FS, yes, but still.
Who of you used S3 to store stuff? And you all wrote your own metadata management system aside of S3. So the only thing that S3 does is it shifts the hard part out to us application developers.
No, I would disagree.
Yeah?
Yeah, please do.
Yeah. Okay, so I mean, storing files on file system comes with big challenges, especially like you have directory limits. You can only store a certain amount of files there. It will get very expensive to traverse the directory tree once it's huge, and that's, I mean, okay, that's handled by S3, and you have to have a good metadata architecture. If you mess up your like file database or whatever for the lookup, then it also gets problematic. I mean, there are downsides, as you said. Deletion is very expensive, also costly for cloud providers. I think deletion is the most costly operation that you can do with S3. Listing is very expensive, so people always think that there are like directories because you can structure it with.
If people think that, they have a problem.
If you like not think about in advance how files are stored, it can be very bad if you have to do listing often. But if you do it well, which needs some experience, it can work very in a way that is not hard to do with like regular files.
You totally agree with us.
Yeah,
because
I agree with everything.
Because yes, you do. Yeah. Because yes, S3 is awesome if you use it as an object store.
Yes, okay.
And if you leave the metadata out of it, if you just say blob this key there, great, that works awesome.
Yeah.
That's how we do it in the current architecture with the S3 object store. We just put the blobs there. But the metadata itself still resides currently in an FSL.
And you always have to do the heavy lifting with the metadata and the structure and stuff like that. But anyway, that's only a side topic.
Like every software-defined storage, like EOS, like CephFS, they all do that. They have a blob store, which works more or less like a key value store, and they have a metadata storage, which simulates more or less a POSIX file system. JuiceFS, which is really neat, also does that.
Have you synchronize or the problem? Can you have both in sync? Or is there a problem?
There is. So we currently we have to currently cache everything in NUTS, and we rely on NUTS. And if now someone changes something on disk in this POSIX case, we use iNotify to invalidate the cache. So and that works for the small systems. That works great. If you use something like GPFS,
also some limits.
yeah, but they work for a local storage. They work for these smaller deployments. They work. If you need to go bigger, then you will no longer use a normal POSIX storage, because then you also have to go to more than one node. So you need a network file system, and then you have something like a GPF GPFS,
GPFS,
IBM
Spectrum
Spectrum Scale,
or ZFS.
ZFS, and they all have a mechanism where you can get all file system events, and we use them to invalidate our caching. And that works nicely.
Yes.
So it's now we go back to the beginning where there is a cache, which you could say is a database. It's not a relational database, but it's a key value store. But it's actually a cache that gets that can be invalidated, not like in the OwnCloud or Nextcloud database where the database is the source of truth, even if the table is called OC file cache.
You could send the prefix.
You could, yeah, you could say the prefix. Yeah. Anyway, so we are basically at the end because that was the journey of what changed in the architecture, what changed in deployment. There are some nice things that we can do with Go that we can't do with PHP. For example, Go is a compiled language, so the kernel will not forbid us to change file attributes. We can actually use file bits and what are they called? File capabilities to allow the OpenCloud process to write a file in the name of another user, for example. That would produce an even tighter integration with the existing users in the file system and the users in OpenCloud. Similar to what maybe if you still know that, like the virtual users in mail systems and actual users in mail systems that are also present in the system.
Yeah, we can do all sorts of interesting and nice things with Go. Having asynchronous things, having long-running processes, all that, of course. As you all know.
Something we weirdly never did with OwnCloud 10, with the PHP code base, because in Laravel you also have like an event worker in the background. We never went there, and I think Nextcloud also still is doing that. But now with Go, we can do all kinds of asynchronous stuff, which is really great. Yeah.
So you removed database, and I get to how you manage the files, but how is the user management done? I think you need some states, some databases, right? You cannot get rid of it completely. But
so
you were cheating a bit.
So we just say that's somebody else's topic. And for the bigger deployments, you will use something like a Keycloak, and they come with a PostgreSQL database. Yay!
So we are back in that game again.
There is that game. However, if you can choose, if you have a company, or even now a lot of homenets have already an identity provider like Autelia or maybe even Keycloak, Authentic. A lot of OpenID Connect identity providers are there. OpenCloud itself does have a built-in identity provider, which comes from Copano. I don't know if we will replace that because I think code is needs to be maintained better. But it is shipped in the binary, and you can just run OpenCloud, and it does come with an identity management. We also implemented our own LDAP server, or lightweight, small, whatever, just the pieces that we need. So it internally is working in memory, and it uses, I think, RocksDB, BadgerDB. So there is a small key value store, which is good enough for what we need to do. There is no, so in the OpenCloud binary itself, there is no relational database, but one or two key value stores.
I guess. Even besides user management, I wonder how you were able to live without features like, I mean, it's a relational database before, you can do queries and so on. So if a user wants to list his files or their files, I mean, I can, of course, walk a file tree, present the directory listing, but
that's too slow.
Expensive. Yeah. I could imagine that naively without the database, I could do that like once and then update it on a notification and cache it and so on. But it seems
so a directory listing
complex.
A directory listing is not that hard. So we do actually go to the NFS or POSIX and say, give me the list of names, so the cheapest version of a file listing. And then we concurrently fetch all entries from the cache, all metadata entries for that direct listing from the cache. So we build directory listings concurrently, and then we render them out.
You can probably cheat it a little bit because it's on the root probably pretty flat, and you can like read the. You don't have to like load the full tree, but just a layer.
Yeah, well, so typically you only, if you browse to the web, you always only list one folder.
Yeah,
and that is.
They benefit a bit from a limitation basically that WebDAV has, because WebDAV by default only lists one directory. And there is a switch in WebDAV and an RFC, I think, even to have an infinite listing, but basically no related server implements that, because it's basically, as you say, it's super expensive to have a full find.
And I mean, WebDAV doesn't have pagination, so that is a problem. So you will run into various limits if you want to list 10,000 files already. You will run into problems.
Okay, one additional question, because the term came, like, how do you do search then without a database?
So the search, whenever you write a file, there is an event that picks up, okay, there's a new file or changed file that gets into depending on the deployment. The bigger ones, it's an Elasticsearch, which is a reverse index. So that is what you need anyway. And the built-in one, there we use Bloody, which is a reverse index in Go, which unfortunately doesn't scale to more than one node. But yeah, that's good enough for a single node deployment.
Which is kind of a database.
It's a reverse index.
So we are mimicking databases everywhere, basically.
Yeah. It's the thing that we got rid of is the huge file table cache that could run hot.
Mm-hmm.
So the key value stores are far more efficient with that. And what we also did, because in Go we can now have a long-running processes in the background. If somebody writes a file, we can say, yeah, we got the data, and then we can internally propagate the change up the tree and actually collect changes and aggregate them. So if you upload 3,000 files to a folder, we no longer have to update the parent folder and the root item 3,000 times each. We can just collect them. And we say, okay, per second, I think we waited 500 milliseconds or something. Something still has changed. I'll just wait a little bit. And then if nothing comes in, then we propagate the change to the root, which is absolutely good enough for the desktop client to pick something up. You don't expect a file change to happen immediately. If you just wrote it, you will first have to either notify someone via chat or via email, probably send him a link, and until that happens, he will have the most recent version.
Yeah, we talk seconds, not hours or so. Maybe some benefit that we could finally implement when we switch to Go is what we call post-processing. So from my client developer perspective, we always in the PHP time, the client uploads a file and then the server does its thing, is first updating indexes and stuff, but also does maybe a virus scan. Virus scan over 4 gigabyte file takes its time. Since PHP is completely synchronous, the client is waiting until that is finished. So that is super annoying, because that is performance that users feel. So it takes time until the file has arrived on the server. So with the new architecture, we changed that, and basically now it's from the client perspective, it's like as soon as the last byte of the file is uploaded, the file is there. And then the server can do whatever it wants. And at some point, for example, virus check. And at some point in time, this file is checked and it's really valid and okay. And then it just changes an HTTP status code in listings, for example. So as long as it's in this asynchronous check, the client sees it as 425, which means come back later or something. I don't know really, but it signals the file is there. I know it. It's secure, but it's still in this post-processing. And that speeds up client interactions, obviously, and gives a way better feeling and processing. And that was absolutely not possible at all with PHP. And now that is really nice because we can do all kinds of things in this post-processing.
Did they not
I
manage?
would like to know if you also experience any downside switching from PHP to Go.
Yes.
Yes.
We lost a lot of applications from the old OpenCloud 10 world. But
And
other than
for me, so I'm coming from background of, I worked 16 years for SUSE in SUSE engineering. And what happens with Go is, now we start to argue here. In PHP, distributions package most of the packages for you. So at least back in the days, let's say. So there was every PHP module was somehow packaged and taken care of by the distribution. Now in Go world, this is all shifted to us Go developers, because every dependency that your code has is now on your table. So whenever there's a security flaw, some problem, it's with us, and not longer the distribution is taking care of your LDAP client that this is cool. That is a real downside of it's a pro and a con of Go, obviously, because it's all easier and we are in control. The developers always want to be in control, but it also puts you in responsibility against users and customers. So that's one downside from my perspective.
Yeah, absolutely. And that is something that will actually that puts a lot of work on our table in the future, because there are requirements from the EU where we have to provide a bill of materials and yada yada yada, and that does bind people's time, and it's not useless, but a lot of things that is then used for is just having a check mark. Oh yeah, we have a bill of materials. Nobody's looking at it, so that's annoying. Yeah, but you have it. Great.
Yeah, but yeah.
Compliance. But and of course, I mean, we lost a lot of applications back then, but I'm really happy because now our web team has started a new, or the web UI has an architecture where we can actually add applications again, and extensions, I think they call it. JavaScript-based client-side applications, which are great. And if you really want to have something on the server, if you need something on the server side, you can deploy a dedicated service. Then you can do that.
Yeah. Which we actually did. For example, we got a lot of critics that we do not have a CalDAV and CardDAV backend, and Nextcloud has it, and that's so nice, and everybody needs it. Which is, I mean, no doubt about that. So we decided to, for the time being, use a project that's called Radical. I don't know, maybe somebody knows it. It's a Python CalDAV and CardDAV backend, basically. And we included it in our setup so that we now have the CardDAV and CalDAV, and that integrates very smoothly in our, especially in the Compose deployment, and it's just there and works. And yeah, so that is easily possible, but that is more because of the architecture in general, not so much of the language.
There was actually one of the reasons also to move away from PHP to Go, because there was always the risk that whatever application you added to your PHP code base could bring down the whole server. Mm-hmm. If there was a bug in there, it would kill your server, and that was annoying. And obviously with this microservice architecture or service architecture or Go precompiled binary, it's way harder. And that's really nice.
I don't say it on the recording.
Okay. Any more questions, please fire away.
Maybe one last question for the recording, and then we can stop the recording, and
then we can.
Okay, yeah. All right. I wonder, do you have like any rough numbers about how much less resources OpenCloud in comparison to the old cloud uses, and how much better it performs? Because that's like from my experience, switching from PHP to Go to services, there was a huge difference, especially in like lower resource usage and number of concurrent connections that you can do.
The official answer on that is yes, we are way more performant. The question is really, where does this gain of performance come from? We have a different web client. We have asynchronous processing on the server side. We have the Go stack. We tried hard. We use this K6 testing that Jörn mentioned before to really come up with reliable performance comparisons between Nextcloud and OpenCloud, but it's really hard to really make the point how faster we are.
It's really hard to extract or to infer reasons from just the numbers. We are way faster in some aspects, and we are slower in some others, and that is not fully explainable.
So you can imagine that I got so much pressure from management and marketing and give numbers. It's really hard. Users constantly and always say the system is much more performant and so it's if you try it, you feel the difference immediately, but that has so many different reasons.
A completely different web UI meanwhile. And we got rid of a lot of these problems that architecture in the code base, not like, okay, do we use an event queue or not, that kind of architecture, but the way we actually deal with files and we handle sharing in how these things are implemented. That's a very big change, and it's really hard to compare these things now. Just from the numbers, yes, we can easily win in certain aspects.
And the other aspect also is Nextcloud is a very, very well done system meanwhile. So the colleagues there, they worked like 10, 15 years now on all these topics. So it's really mature in that regards. And we are competing there. It's an interesting challenge. I think what we can say is that we're very that resources, hardware resources, there's a benefit on our side as well. So
yeah, if you don't deploy it like that,
yes,
if we can agree on that. So I'm looking forward to so we are running this like that, and I'm really glad that we did that. We are running performance tests, we're running load tests with that, and it's very, very nice.
Get rid of excess. Yeah. And synchronous mode.
Yeah, but we are deploying things like that currently, and the tests are working really great. So
yeah.
So just before I stop the recording, thanks very much for this. Really, thank you.
Thank you.
No, fireside chat. It was really a very engaging, format, I feel. So with that, I stopped the recording and
yeah, thank you.
Thank you.
It was nice being here.